So let us discuss compact subsets. And to start, let us recall the well-known Heine-Borel theorem in the case of Euclidean spaces. So consider a subspace of k to the n, where k is either the field of real numbers or k the field of complex numbers. Of course, the Heine-Borel theorem is usually stated in the case of the Euclidean spaces R to the n, but you can also have the version in C to the n, knowing that this K to the n is isometrically isomorphic to a Euclidean space, that is R to the n times the dimension of K. And in this case, you have, let's say, the dimension is 2 if k is equal to c, and the dimension is 1 if k is equal to r. So this k to the n can be isometrically embedded into, or it is isometric to a Euclidean space. So compactness in R to the n is equivalent to being closed and bounded. So take note here, we have a finite dimensional vector space. So the question would be, how about infinite dimensional spaces? Can we say that a compact subset is closed and bounded? Is the converse of this statement also valid? Well, later at the end of this lecture, we will see that this is not the case. This equivalence is not valid in infinite dimensional spaces. However, it can be said that the implication, meaning if you have a compact subset, then it is closed and bounded in the case of metric spaces. So this implication is valid in the case of metric spaces. So a compact subset of a metric space is also closed and bounded. So for the proof, you may consult a standard text in topology. So to proceed, before considering specific examples, let us discuss the following theorem that serves as an alternative criterion or characterization of compact sets in a metric space. So let XD, the pair XD, to be a metric space, and take a subset A of X. Then the following three conditions are equivalent. So A is compact, and by this we mean that it is covering compact. So any open cover of A can be reduced to a finite subcover. This is equivalent to the sequential compactness of the set A. And this means that every sequence in A, let's say X sub n, has a convergent subsequence let's say X and J, and this sequence, or the limit of this sequence, is also in A. Okay, so this is what do we mean by sequential compactness. So every sequence has a convergent subsequence, and the limit is also in A. So recall that this situations are somewhat typical for metric spaces. For instance, continuity can be, or continuity is equivalent to sequential continuity. Closeness is equivalent to sequential closeness. So this is also true in the case of compactness. And finally, these two statements are equivalent to the completeness of A. That is, every Cauchy sequence in A will converge to an element in A, of course, with respect to the metric D restricted to the subset A, as well as it is pre-compact. In other texts, the word pre-compact is sometimes called relatively compact. And by this, we mean that you can find a covering of your set by a finitely many balls. Given a positive epsilon, there exists a sequence x1 to xn in A or in X, such that A is covered by the union of the balls centered at x sub j, j from 1 to n, having radius epsilon. This is what do we mean by pre-compactness. So the centers are not necessarily in A. Okay? So it can be in the ambient metric space X. And in general, this number n, the number of points or the number of centers, depend on the given epsilon. And probably, or in general, the smaller the epsilon, the larger the number of elements that you need. So again, compactness in a metric space is equivalent to sequential compactness, and moreover, it is equivalent to completeness and pre-compactness of the set. For the proof, we proceed in establishing three implications. Namely, 1 implies 2, 2 implies 3, and then 3 implies 1. So let's now start the proof. So for this, let us suppose that A is compact and by way of contradiction, suppose that A is not sequentially compact. So this means that there is a sequence, let's say x sub n, in A with no limit point in A. So this is equivalent in saying that your sequence does not have a subsequence which converge to an element in A. Now, for each, let's say, positive epsilon and y in A, okay. Let us denote the set n sub y, the integers, or the set of integers. So these are the indices. wherein the x sub j is in b sub y epsilon. Okay, so to have an idea of the succeeding statement, so let us consider an open ball centered at y having a radius epsilon. So this y is not a limit point of your sequence. So y, since it is in A, it's not a limit point of the sequence. This means that this ball, or there exists. So we should replace this by the following. So first pick an element A and Y, then there exists, let's say, or that is correct. So okay, so given this epsilon, this must contain only a finite number of elements of your sequence xn. Okay. Otherwise, if it contains an infinite, then you can reduce the ball. Then this would be a limit point of y. This y would be a limit point of xn, which is not the case. So in other words, if it contains a finite number of elements in xn, then this is finite. Okay. The epsilon can be large, so that's why we need to replace this by the following. So let y be in A, then there exists, let's say, epsilon sub y, positive, such that we need to replace this by sub y, such that this one is finite. Okay, so this epsilon depends on y. So you take this epsilon sub y to be sufficiently small in order that this ball contains only a finite number of elements of your sequence. So this n sub y is finite. So we collect these balls, okay. We know that this is an open cover of A, since the center is contained in A. By compactness of A, we can reduce this to a finite subcover. So there exists, let's say, y1, y up to y sub k in A, such that A is covered by the union of the balls centered at y sub, say y sub j, epsilon y sub j, j from 1 to k. Now, for each n, we know that our sequence is in A, so xn is in A, hence xn must be in some ball. Okay, so for some, of course, for some j from 1 to k. According to the definition, then this index n must be in n sub y sub j. So n must be in n sub y sub j. Thus, okay, so for here n of course is a positive integer. So given a positive integer, we have established that this is in n y sub j for some j. This means that n is a subset of this union, j from 1 to, let's say, k. And now here is the contradiction. We know that this is finite, so therefore the union is also finite. This is not possible because we know that the set of positive integers is infinite. Okay, so we arrive at the contradiction. So based on this, the culprit here must be that the assumption of being not sequentially compact is false. So therefore, A must be sequentially compact. And this proves 2. Next, let us consider this direction. So for this direction, let us assume that your set is pre-compact, or I should say sequentially compact. We wish to show that A is complete and it is pre-compact. So for completeness, let's start with a Cauchy sequence in A. And according to sequential compactness, one can find a subsequence, let's say x and j, for which this sequence converges to x for some, let's say, x in A. So here we have a Cauchy sequence with a convergent subsequence. We know that in the case of metric space, the whole sequence must also converge to x. And this implies that A is complete. So that's the easy part. And we replace this by, of course, there should be 3. Now, for pre-compactness, again, by way of contradiction, suppose A is not pre-compact. So this means that there is some positive epsilon such that A cannot be covered by finitely many balls with radius epsilon. So if you cannot cover it by finitely many balls of radius epsilon, in particular, this implies that A must be infinite. Take note that if this is finite, then you can just take the ball centered at the points on the finite set, then you will cover A by a finite number of open balls with radius epsilon. But this is not the case. So therefore, A must be infinite. So to get the idea of the proof, what we do is the following. So suppose this is a portion of our set A. We will take a point x1 with and then consider the ball centered at this point. So the radius here must be, say, epsilon. Okay. Since it is impossible, or it's not possible to cover A by finitely many balls, there must be an x2 that is outside this ball. Okay. So again, we construct the ball centered at this point. Since A cannot be covered by finitely many balls, there must be another ball, okay, or there must be another element of A that is outside these two balls. So again, you end up with another point, let's say x3, and then constructing this ball at x3 having radius epsilon. And you see, you continue the process inductively. So let us write it down. So let us pick x1 in A. So this means that there exists an x2 in A such that x2 is not an element of the ball centered at x1 with radius epsilon. Because otherwise, if any element in A contains or is contained in this ball, then you can cover A by this single ball, which is not the case. So suppose x1 up to, let's say, x sub k has been suppose these were chosen. Now we take x sub k plus 1, the next, okay, such that x sub k plus 1 is not in the previous balls. So x sub j epsilon for every j from 1 to up to k. So by construction, we see that your x sub L is not in the bx as long as L is greater than k. So the previous, for the index L, if you take a smaller index, then your x sub L should not be contained in the previous balls. So this means that the distance between xl and xk is at least greater than epsilon. So this implies that you cannot have a convergent subsequence of this one. So this has no convergent subsequence due to the fact that the terms of your sequence are not close to each other. More precisely, they are at least epsilon apart. So the distance between two terms is greater than or equal to epsilon, greater than or equal to epsilon. So they cannot converge to a point, and hence to a point in A. And from this, we obtain that we have a contradiction, since we assume that A is sequentially compact. So for the last implication, so that's 3 implies 1. So here, we assume that A is complete and pre-compact. So we wish to show that A is compact. So let's start with a covering of U, or I should say a covering U indexed by lambda of A. Due to pre-compactness, so given a positive epsilon, I can find, let's say, points. Let us name the points with tilde. So x tilde 1 up to x tilde n in X, such that A is a subset of the union of these open balls. So this is basically pre-compactness. Let us introduce a collection of subsets of A. So consider the subsets of A for which B cannot be covered by finitely many elements of your covering U. So here you take the collection of subsets of A wherein you cannot reduce your open covering into a finite subcover of B. We claim that A is not in this collection script A. So this means that A can be covered by finitely elements of U, therefore it is compact. So to prove our claim, suppose, so by way of contradiction, suppose that the claim is not true. So what if A is in script A? This means that A cannot be covered by finitely many elements of U, therefore A is not compact. Suppose this is the case. Given an element B of A, script A, we claim that there exists an X, some X in your sequence of centers, X of J, okay, such that B intersection B, let's say X epsilon, is also in A. So in other words, if B cannot be covered by finitely many elements of U, then intersecting this B by an open ball in the covering of A, by that we mean this one, it is also an element of A, script A. That is, this intersection cannot be covered by finitely many elements of U as well. Well, to see this, indeed, if this is not the case, in other words, if this is not in A, for every X in this collection of centers, then we can write first B as B intersection A. Take note that B is a subset of A, therefore B intersection A is the smaller set, which is B. And take note that A is a subset of this one. So applying the distributive law, this is subset of B intersection B, the ball centered at X tilde J with radius epsilon, J from 1 to N. According to this statement here, so this means that this can be covered by finitely many elements of your collection U. So since this is a finite union, this implies that B can be covered as well by finitely many elements of U, just combining all those elements in U that cover this set. So that is B is not an A. So if this is true for every X in this set of centers, then we know that B is not an A. So you just apply the contraposition. In other words, if B is an A, then this intersection must be an A for some X in your sequence of centers. So we are now guaranteed with this one. So based on this, we recursively define the sequence B sub, let's say B sub k, k from 1 to infinity. This is a sequence in script A as follows. So B1 is equal to A. Okay, we know that I should say BK not in A. B1, let us set B1 to be A. And here, suppose that the claim is not true, so A is in script A. So again, this must be an element. Okay. Now, for K greater than or equal to 2, we define B sub K to be the previous set. Then you intersect this with, let's say, bxk minus 1, 1 over k. Okay, so in particular, here you take epsilon to be 1 over k, and this xk minus 1 must be in the sequence of centers. So in general, they are in X. This is well defined because we said that if B is in A, then you pick an epsilon, you can find the intersection of this B with a ball is also in A. So you take this B as the previous set and you define recursively. And by modifying your epsilon to be 1 over k at each step. Okay, so what we do is we pick an element. So for each k, let us take y sub k in b sub k. Now for, let's say, of course, we know that this b sub k is in A, since we started with the set A. So all of this must be a subset of A. Now for L greater than or equal to K, if we compute or we estimate the distance between YL and YK, this is less than or equal to the distance between, let's say, YL and XK minus 1. So you apply the triangle inequality Y sub K. And take note that for the second term, this is in the center, okay? And Y sub K is an element of B sub K. So if you are in B sub K, the distance between the center xk minus 1 must be less than 1 over k. So that would be the second term. On the other hand, this YL, you know that YL is BL. If L is larger than K, then this is also a subset of B sub K. Since our construction here implies that this one is contained in BK minus 1. So your sequence is decreasing. This means that the larger the index, the smaller the set. So again, if YL is in BK, then the distance of this point YL with respect to this center again is less than 1 over K. And we know that this tends to infinity as K, well, it is independent in L, so as well as L going to infinity. So we have established, or at least constructed, a Cauchy sequence X or A because these elements are in A, and by completeness of A, this must converge to Y for some Y in A. So to have an idea, let us consider the following figure. Okay, so consider this set BK minus 1, in particular this region here as your BK minus 1. And you take the ball centered at xk minus 1. Take note that the x sub k's, the centers are not necessarily in the set A, having a radius 1 over k. And in that case, the intersection, this would be B sub k. So this is our definition of B sub k. Now, we took an element y sub k, and in this case, let us also consider this y sub k with a ball that is twice the radius of your ball centered at x sub k minus 1. So this will be, let's say, 2 over k. Now, take note that this y sub k, well, let's say for k large enough, we can say that this is close to some point y. Where what is y? Y is the limit. So this will converge later to the point y. And for this, we consider, let's say, a radius delta that is contained in this blue region here. Consider the ball centered at y. But now this one has radius delta. And what is this delta? This delta can be large. Okay, So let us consider a larger ball. So the ball can be quite large. And let's do something like this. Okay, that seems okay now. So let's say this is, let's imagine that this is the radius delta. Okay. Let us first start with the fact that there exists an index lambda such that y is in u lambda naught. What is this u lambda naught? This is an open set in your covering u, script u. So by we're using the fact that this is open, there must be a radius delta such that the ball centered at y with radius delta is contained in u lambda naught. Based on this construction, well, you can establish using the triangle inequality that b sub k, by definition, this is a subset of b sub x minus k, 1 over k. And then you can show that this is contained in the ball with radius, let's say, y sub k, centered at y sub k with radius 2 over k. And you can simply establish this using the triangle inequality. Since the distance between yk and xk minus 1, let's say, is less than 1 over k. So if you apply the triangle inequality, the ball centered at yk with radius 2 over k contains this smaller red ball here. Now, for large enough k, this 2 over k shrinks, and this y over k gets closer to y. So this means that we can choose k large enough such that this ball byk centered at 2 over k is contained in by delta. And we know that this is a subset of u lambda naught. This implies that b sub k is not an A. Why? Because we have covered this this b sub k, this region here, okay, by a single ball, this one, with radius delta, and that ball is contained in some set in your covering script u. In other words, we have reduced the covering by a single cover. So b sub k is not an A. And this is again a contradiction to our construction that b sub k is, where's that? Here. So if you look at this line here, b sub k is in A. So that's a contradiction. So this means that, okay, going back to our claim, so we suppose that the claim is not true we arrive at a contradiction. So therefore, this means that this assumption is not valid. Hence, A must be not in script A. And based on this definition of script A, you take the negation of this A can be covered by finitely many elements of U. Hence, we have reduced this open covering by a finite subcovering. And since this is an arbitrary covering of A, this is valid for any covering, therefore A is compact. And this establishes the implication that is 3 implies 1. In other words, completeness and pre-compactness imply compactness. And let us state some remarks. So in the assumptions of the previous theorem, so if A is a subset of a metric space and this is pre-compact, and B is a subset of A, then B is pre-compact. So a subset of a pre-compact set is pre-compact. That follows immediately from the definition of pre-compactness. So you can cover A by finitely many open balls, given a positive radius. Then that covering can be used as a covering of B as well. If I have, let's say, a finite sequence of pre-compact sets, say A sub 1 to A sub n, then the union of these pre-compact sets is again pre-compact. So the basic idea here is that since each A sub j is pre-compact, you can cover that by finitely many balls given a radius, given as a positive radius. Then you just combine those open balls to have a covering for this finite union. So take note, since you have a finite sets, then the union of a collection of finitely many open balls is again finite. Next, if A is, let's say, pre-compact, then so the closure is compact. I should say pre-compact. To look at the proof. Okay, so replacing epsilon by epsilon over 2 in the definition of pre-compactness, which is of course still positive. So given an epsilon, there exists x1 up to xn in capital X such that A is a subset of the union, let's say epsilon over 2, j from 1 to n. And taking the closure, so the closure of the smaller set is smaller than the closure of the larger set, which is the union. Well, the closure of the union is a subset of the union of the closures. Since the closure of this ball is the closed ball, and the closed ball with radius epsilon over 2 is contained in the ball with radius epsilon, you end up with the pre-compactness of the closure. Now, in the case, let's say if if X is complete, then A is pre-compact if and only if the closure is compact. So this is why sometimes we call the set pre-compact. So before it is compact, so if you take the closure, you will get a compact set. For the proof, let's say, so in this direction, if A is pre-compact, then A bar is pre-compact by the third remark. Okay, the set is pre-compact, then the closure is pre-compact. So A bar is a closed subset of the complete metric space X. This implies that A bar is also complete. So a closed subset of the complete metric space is also complete. And we have discussed this last time. So combining these two, so pre-compactness and completeness, thus A bar is compact. Here you use the fact that 3 implies 1, or in fact they are equivalent in the previous theorem. On the other hand, if A bar is compact, then it is pre-compact and complete. Okay, so we do not put the completeness in this case. Pre-compactness would suffice. Since A is a subset of the closure, A is also pre-compact. And this is from our first remark. A subset of a pre-compact set is pre-compact. So again, in complete metric spaces, pre-compactness is equivalent to the compactness of the closure. Under the special case of k to the n, which is complete, then A is pre-compact if and only if the closure is bounded. And this should be remark 5. Here, you just apply the previous remark and the Heine-Borel theorem. Indeed, if A is pre-compact, then, according to our previous theorem, the closure is compact. Therefore, by the Heine-Borel theorem, it is bounded. And vice versa, if A bar, the closure of A is bounded, since the closure is already closed, A bar is compact. So the closure of A is compact, therefore A is pre-compact by applying 4 once again. And finally, the image of a pre-compact set under a uniformly continuous map between two metric spaces is again pre-compact. So let us state that precisely. So I have two metric spaces, X and Y. And a map, let's say F from X to Y that is uniformly continuous. If A is a subset of X and this is pre-compact, then the image, which is a subset of Y, is pre-compact in Y. So pre-compactness is invariant under uniform continuous functions. That is, the image of a pre-compact set is again pre-compact. There are examples wherein continuity is not sufficient. So uniform continuity is needed. Going quickly with the proof of this theorem. So given an epsilon, there exists a delta such that if the distance between, let's say, x1 and x2 in X is less than delta, then the distance between the associated images is less than epsilon. This is basically the uniform continuity of your function f. Now, according to the pre-compactness of A, so for some, let's say x1 up to x sub n in X, A must be, or A can be covered by the ball centered at x sub j, j from 1 to n, with radius delta. Okay, since delta is a positive. Now, if I take an element of the image, so that is y is equal to f of x for some x in A, then there exists a j from 1 to n in such a way that since x is in A, it must be in this union, therefore x must be in this ball for some j. So the distance between x and xj is less than delta. And applying the uniform continuity here, we see that the distance between f of x and fxj is less than epsilon. In terms of the open ball, this is f of x is in the ball in y, having center at fxj with radius epsilon. Thus, we pick an element in f sub a. We have established that this image is in fx, or is in this ball for some j. So in terms of inclusion, this means that f sub a is a subset of the balls centered at the images corresponding to the center of the covering in A. So we have covered the image by finitely many balls, and therefore the image is pre-compact. So in the next lecture, we will discuss the Heine-Borel theorem, or is it possible to extend the Heine-Borel theorem in infinite dimensional spaces?